In this video, we will discuss about the concept of moment of inertia and its physical significance. So here if you try to break the first part and observe, right, this term inertia we have already discussed in the laws of motion. So what does this word inertia actually mean and what does it signify? So inertia is basically the opposition offered by an object to the applied force. So I repeat it. If there is an object like this and you apply a force on that object, if this object is offering a resistance to the force that you are applying, you call the property of opposition exhibited by this object as inertia. And we have seen that the physical quantity which is responsible for the inertia of an object is its mass itself. So that is in the case of translational motion. Now, an important question to be asked is, what if I use the word moment of inertia? Right? So, inertia, we understood that it is basically the opposition offered by the object to the applied force. Then, what do we mean by moment of inertia here? To give you a hint of it, right? Whenever this concept of moment comes, it is something related to rotation. So, have this in your mind whenever you see the concept of moment force, linear momentum, linear momentum. If you see the word moment, right, it is related to rotational motion. In a similar way, here moment of inertia is related to rotation, hence it is also called as rotational inertia. So I hope this concept is clear. Now, I need to explain what exactly this rotational inertia means. So, if you just use the word inertia, it is understood that the opposition is offered to the applied force, and we know the fact that force is always responsible for the translatory motion. So, force will always cause translatory motion in the object, whereas torque will always cause rotational motion, right? So, torque will always cause rotational motion. Hence, if I combine the word rotational inertia, it gives me a hint stating that it is the opposition offered by the object to the applied torque. So, what does it mention? It is the opposition offered by whom? It is the opposition offered by an object to whom? To the applied torque. Right. Now, having said this, let us try to understand how exactly it is going to, or how we can feel the concept of moment of inertia. Try to understand this. So, if you hold this pen, right, let's say you take your pen and start rotating about its center of mass, and it will be easy for you to rotate. But if you take the same pen and try to hold it at some other point and rotate it horizontally, you cannot do it as comfortable as you did with respect to the axis of rotation being the center of mass. There is a reason for it. The reason for it is, when you take the center of mass, the mass is equally distributed on both the sides. That's what the significance of center of mass is supposed to be, right? But if you take any other point other than the center of mass, then you are redistributing the mass in such a way that one side it is heavy and the other side it is less, due to which you are not able to rotate it as comfortable as you were able to do it in the case of the axis of rotation being the center of mass. Having said this, what I am trying to tell you here is this opposition offered by an object to the applied torque is there, right? It has something to do with the distribution of mass. That is the reason I gave this example. Now try to understand. I'm going to give you the mathematical expression for what exactly moment of inertia is going to be and how is it supposed to be measured. Now, if I take this to be the axis of rotation, and with respect to this, if I say there are multiple masses, m1, m2, m3, so on till Mn is there, where M1 is at a distance of R1, M2 is at a distance of R2, and M3 is at a distance of R3, and Mn is at a distance of Rn. Now you can ask me a question, aren't the mass supposed to be on this side? They can be, right? I've just taken the masses on one of the sides. And observe, all these are point masses. They are not extended masses. They are point masses. So, having this in mind, I am going to write the mathematical expression for moment of inertia. Observe this, moment of inertia is represented by the symbol capital I. So, capital I, that is the moment of inertia, is given as the product of, I repeat it is the product of mass of a particle multiplied with the square of its distance from the axis of rotation. That is, mass of the particle and square of the distance of that particle from the axis of rotation. So, that is going to be the moment of inertia of the first particle, right? This is how the moment of inertia for each particle is written, but I considered a system of n particles. So, the moment of inertia of these n particles is given as n1 r1 square plus m2 r2 square plus so on till mn rn square. I hope it is clear that you multiply the mass of an object with its corresponding distance raised to the power 2, right? So, to just put it simple, right? This is actually the moment of inertia of the first particle. M2 R2 square is the moment of inertia of the second particle. In a corresponding way, Mn Rn square is the moment of inertia of the nth particle. Okay. Having said this, this is the formula for moment of inertia, and I have clearly mentioned that this formula is applicable only for point masses. It is not applicable for extended mass. Now the question is, I took the spin and I explained it. If you see, this is actually an example of extended mass. So if you ask me a question, is it not possible to measure the moment of inertia of the spin? The answer is, I didn't say that. I didn't say that you cannot measure it. You can do that. But for that, what you need to do is, instead of summation, we are going to follow the process of integration. Okay. So, how to calculate the moment of inertia of extended object is, how to calculate the moment of inertia of the extended object is something like this. I is equal to, you write integral of r square dm, right? So, dm is the one which is considered to be the point mass on the extended mass, one of the point masses on the extended mass, and r square is the square of the distance of that point mass dm from the axis of rotation. So, just to give you an example, let's say I take this rod, okay, I take a rod like this and I have a mass dm present here, and let's say this is rotating about this axis, and let me say that this distance is going to be r. Then how you write this? You write it as I is equal to integral of r square into dm, and when you solve it, you will get the value of dm in terms of r, and then you need to integrate it with the proper limits. So, as we progress through the derivations, I will explain you how we can use this formula. So, just to summarize it here, I hope it is clear with the fact that moment of inertia is also called as rotational inertia, and it is basically the opposition offered by an object to the applied torque. Means when you try to rotate an object, whatever is the opposition the object is providing to the torque that you apply is what is called as moment of inertia, and that is a property of that particular material. And the formula for moment of inertia is, it is defined as the product of the mass and the square of the distance from the axis of rotation of that particular mass, right? So, when you know the moment of inertia of individual particles, if you want to calculate it for the system, you are going to use this formula. And if you want to calculate the moment of inertia of an extended object, then it is given by the expression I is equal to integral of r square dm, where r is the distance from the axis of rotation to the point mass dm that we have considered on the extended object.